What will happen here? Here again we shall construct some functional on the space of continuous functions on gamma, and we shall prove that it is non-negative and invariant. Then it will coincide with some higher measure, and so the outline is like this. Well, okay. Okay, so let f be in this space B1 of G, so that it is integrable and representable in the following form. And I will always write mu with the subscript f here in this formula, and take any function h in L1 of G. Then first we write some triviality, so the convolution of h and f at 0 is the integral over G of h of minus x f of x dx. So here should be 0. So, okay. Now I write what f is. What f is. And f is represented in this way. So this is the integral over G, the integral over gamma h of minus x gamma of x mu f of gamma dx. It seems to be that everything d. Nothing is missing here. And after this, I integrate first in x, and here recognize precisely the Fourier transform of h. Because if I change minus x by x, I obtain here gamma of x bar. Okay, so this is equal to the integral over gamma of h hat of gamma d mu f of gamma. Okay. So we have this formula. Now I need another simple formula. So I will use the fact that this quantity is equal to this one, and I will apply this to the Fourier transform of some convolution. So let G be another function in B1 of G, and let's calculate the following integral over gamma of f hat G hat d mu f. Here f is the same as before, and g is another function. Not f, h. H is the same as before, so h is some function in L1, g is another function in L1, so we calculate this integral, and this is none other than the Fourier transform of the convolution of h and g. Yes. f. And now we apply this formula to that integral with the convolution of h and g in place of h. So it turns out that this is equal to h convolution with g, convolution with f, and all this at 0. Yes? Now the convolution is commutative and associative, so we obtain h convolution with f, convolution with g, and all of this at 0. When we apply the same in the reverse order, we obtain the integral over gamma h hat f hat d mu g. Yes? And now look here, h was an arbitrary function L1. So we have this measure with this density and this measure with this density, and when we integrate these two measures with an arbitrary, the Fourier transform of an arbitrary function L1, we obtain the same. And since these Fourier transforms are dense in C0 of gamma, we see that simply g hat d mu f is equal to f hat d mu g for every f and g in the space B1. So these measures are identical. Now we are going to define some functional on the space, I use the space of functions with compact support on gamma. In fact, it will be extendable to C0 of gamma, but for the time being, I use only compactly supported functions. The definition will be a little bit tricky. I shall use this formula to define it correctly, to define it unambiguously, but we need some preparations. Simply let psi be a compactly supported continuous function on gamma, and let k be its compact support. Then take some point gamma 0 in k. Then there is a function u in such that, compactly supported function on G such that u hat of gamma 0 is not 0. Why so? Because this is quite easy, but why?
Well, if it's not, then gamma is equal to 0.
Sorry?
If it's not, then gamma is equal to 0.
No, gamma is not equal to, no. Well,
It's the same as gamma of u, right? If it's gamma of u and it is always 0 for all u is
yes, sure. If this is 0 for all u, this means that the linear functional, continuous linear functional, this is also multiplicative, corresponding to gamma 0 is 0, so but it is non-zero always, so this is the reality really. Well, now take this function u and consider the function u convolved with u tilde, where this tilde is the same as it was before. This is a function. What do we know about this function? This function is positive definite. This function is positive definite. This we calculated when we defined positive definite functions. If we take a function L2 and consider this thing, then this is positive definite. This is very easy calculation. We really did this. This is an important moment because we use here some positive definite function which is a priori not of the form, is not represented by the integral of positive measure. Yes. So this is positive definite. And also is Fourier transform. We know that this is equal to the modulus of u hat squared. So this is positive at gamma 0. So then it is positive in some neighborhood of gamma 0 because this is a continuous function. Convolution of two functions L2 is continuous. So for every point gamma there is a positive definite function of this sort whose Fourier transform is positive in some neighborhood of this point. And then it follows that we can find a finite number of such functions so that their sum is positive on k. So g is equal to u1 tilde and moreover, still this function g is in B1 of g. So it is positive definite not it is positive on k, but g hat is positive on k. Now it is positive definite, and also it is integrable because it is completely supported. So u1 is completely supported, this function is completely supported, so the support of this function is also compact, and so on. So it is in L1. Now this function is in our space. We now define our functional t on this function psi. So we simply put, by definition, this equal to the integral over gamma of psi divided by g hat d mu g. And mu g is the measure that represents this positive definite function. So in a way, this is a non-trivial point, because we learn that this function is positive definite from some external properties, and then we use the Bochner theorem and obtain this measure which represents it. Okay? So this is consistent because G is positive on the support of C, and if it is positive, it is even bounded away from 0 there, because it's continuous. So we may write this formula, and in fact, this doesn't depend on the choice of G because of this identity. So let's write it down. Let f be another function in B1 of G with f hat non-vanishing on K. Then okay. We can artificially incorporate f in this formula. We may write that P of C is equal to the integral over gamma of psi f hat g hat in the denominator, then we write f hat is the numerator, and we write this measure, and this is the same as there, and after that we use the fact that this thing is equal to this thing. Now this g hat cancels, and we obtain this integral. So we can use any function non-vanishing k in this definition. So this is a well-defined functional, clearly it is linear. How to prove that it is linear? Simply, if we have two functions, say psi1 and psi2, then they have compact supports. So we take their joint compact supports, the union of their compact supports, and we produce a function g corresponding to this union, and then use simply this formula, and we see that it's linear. Okay, so it is linear. Then okay. Our initial function g, well, we have proved that we can write such a formula for every function f that is non-zero on k. But our initial function g was positive definite. And so this measure is non-negative by the Bochner theorem. And this implies that t is a non-negative functional. If psi is non-negative, then t of c is also negative, so t is non-negative. Now we also, it should be observed that this function is non-zero. So what we want to prove that it is translation invariant, and then it will be represented by the Haar measure. Well, but to really obtain a Haar measure, we also need that this function will be non-zero. Okay, so this is also easy. Take f in B1, which is non-zero, then mu f is certainly non-zero. Well, and since it is non-zero, then we have the following, that integral of psi d mu f is non-zero over gamma for some psi in the space. And then we can write the following, that T of psi f hat is equal to the integral over gamma psi f hat over g hat d mu g, and this is equal to, so f hat d mu g is this guy. So this is integral of gamma psi d mu f, and this was chosen to be non-zero. Okay. So, well, in any case, this could not be non-trivial, but still some argument is required here. So just to find some function which is this function of non-zero, now what we need to prove is the invariance of this function under translation. Here it seems to me that we need something like that. Maybe I demand too much, but anyway. So K as above, we can construct G as it was here, in this way. So that G hat is positive on some wider set. Namely, it seems to me that we require the positivity on K united with K plus gamma. Also I take some point gamma in gamma, gamma 0 in gamma, simply will explore the shift of this psi by gamma and prove that the value of the function is the same. So fix some gamma and so let's suppose that this function g is G hat is positive even on this big compact set, K and two shifts of it by gamma 0 and minus gamma 0. Probably some of them is not required and cannot guess immediately. Now consider this function g and introduce a new function f, which is equal to gamma 0 of minus x g of x. So simply multiply this function by a character. This is the same as gamma 0 of x bar gamma of g of x. The same. Well, okay. First, we need the formula for the Fourier transform of this function f, and this is quite easy. We already calculated this thing, so let's repeat, f hat of gamma is equal to the integral over g gamma of x bar, gamma 0 of x bar, g of x dx, and this is none other than g hat of gamma plus gamma 0, okay? So the Fourier transform obeys this formula. Now I rewrite what f is in terms of this representing measure for the function g. I remind you that g is positive definite, so it is represented by some measure. F of x is equal to gamma 0 of x bar, integral over gamma of x d mu g of gamma. Okay? And after that, we simply write this way, the integral over gamma of gamma 0, gamma minus gamma 0 of x d mu g of gamma. So this bar, when I put this under the integral sign, this transforms into minus here. Yes? This bar transforms into minus here. So this will be equal to the integral over gamma of, say, let it be some new variable called rho of x d mu g, which is shifted. So the shifted measure mu g. If I claim that this is a new variable, then gamma is equal to rho, then gamma is equal to rho plus gamma 0, so we have this. Now we take our function psi, which was supported in k, and let's shift it. Let psi 0 of gamma be equal to psi of gamma plus gamma 0. Okay? And I want to prove that T of psi is equal to T of psi 0. And this will prove the invariance of our functional. Now, what is T of psi 0? T of psi 0, by our basic formula, is equal to the integral over gamma of psi of gamma plus gamma 0 over gamma hat, g hat of gamma d mu g of gamma. So this is precisely the definition, and we use the fact that g is appropriate in this definition because this function psi 0, where is it non-zero? It is non-zero on k minus gamma 0, yes? Okay, and g is non-zero there, so we can use this definition. Now we replace here g by f, which is possible. So f is also non-zero f hat is also non-zero everywhere. F hat is this guy, and it is non-zero. Where it should be. So we may replace g by f. So integral over gamma psi of gamma plus gamma 0, well, f hat of gamma d mu f of gamma. Now f hat of gamma is g hat of gamma plus gamma 0. And about the measure, well, what do we do here? So this shows that this measure mu f is equal to this guy, because this measure mu f is unique and this measure represents f. So we may use right here d mu g of gamma plus gamma 0. Now we return to this variable. We write gamma instead of this, all this. So it is equal to the integral of capital gamma of psi of gamma divided by g hat of gamma d mu g of gamma, and this is t psi. So this is really invariant, and now what does it follow? It follows that t is generated by some Haar measure. Positive, invariant, linear, and so on. Then there is a Haar measure of on gamma.
Why t is positive?
Sorry?
How did you get that t is positive?
Why here I don't well, it seems to me that I need also that G had be positive on K united with this set, and this set, well, this is just for safety.
Yes, I mean, how do you get that t is positive? Why do you have this positive?
Because when we take the initial definition, then G hat in the denominator is positive, because G is a positive definite function. So G hat is positive. Well, G hat is positive simply because it is the sum of convolutions of U and U hat, and the measure that represents G is positive because G is positive definite. And G is positive definite because if we convolve some function in L2 with itself, some function h in L2 with h tilde, then we obtain a positive definite function. So,
okay, so we have that for positive definite function. Yeah, the measure is okay.
Well, okay. So not very difficult, but a bit tricky still. Okay, so there is a Haar measure on G such that T of psi is equal to the integral over gamma of psi of gamma is equal to integral over gamma of psi of gamma f hat of gamma divided by g hat of gamma d mu f of gamma, and this thing f d mu, d mu g of gamma, and this thing f hat d mu g is equal to g hat d mu f. And so this cancels, and we obtain this formula. Okay, so we have this for every function f in L1, and also now we know that this is represented by the Haar measure. So the same thing is equal to the integral over gamma of psi of gamma f hat of gamma d gamma and this is true for every function psi which is continuous and completely supported. So this means these two measures coincide. Okay? And this implies the formula, this is precisely the formula we need. So f of x is the integral over gamma of x d mu f of x, and this is equal to the integral over gamma of x f hat of gamma d gamma. Okay, and this is the inversion formula. Now I forgot to say, probably it is it should be noted that this space B of G, not B1 but B, so the inverse Fourier transforms of Simet measures. This is precisely the set of all complex linear combinations of positive definite functions by the Bochner's theorem. So I remind you that this is the set of all functions f that are representable in the following form: f of x is equal to the integral over gamma of x d mu f of gamma, where mu f is not necessarily positive, every complex measure. So every complex measure is a linear combination of four positive measures. So this guy is a linear combination of four positive definite functions. On the other hand, if you have several positive definite functions, then each of them is represented in this form, even with the positive measure, so the linear combination is also represented. So this is precisely the linear combinations of positive definite functions with complex coefficients. And I want to emphasize that the key point here that we do have some positive definite functions which are a priori which do not emerge as this inverse Fourier transform. So these convolutions of u and u tilde, they are positive definite, and after that we may claim that it is representable in this form, but after that we obtain everything we need. So this is the key point. And now maybe I prove only one consequence of this inversion formula, because the other consequence is the Plancherel theorem. So here the order of presentation is the following. We prove this inversion formula for this strange class B1 of G. Then after that we are able to prove the Plancherel theorem. And after that we prove everything we want. So in the normal presentation with spaces Rn, Plancherel theorem emerges in some other way and after. And here it emerges first. But before doing that, we prove the following thing. So I remind you, well, the definition of so this was how. I remind you the definition of this neighborhoods of 0 in G. This is a set of all x in G for which 1 minus gamma of x is less than epsilon for every gamma in the set C. So you remember this? We proved. Sorry? Another letter point maybe. I don't remember. So if you tell me U and V. Okay, so this is U. Yes, this is U. Okay, and there was something dual in gamma, and K was a compact subset in G. We proved that these sets form a base of neighborhoods of 0 in gamma. And about these sets, we proved only that they are open in G, which is more or less clear. Well, it's easy. But now we are already able to prove that they form a base of open neighborhoods of 0 in G. So let me be theorem.
Actually, the notation was U with two sub-indices.
Maybe let it be this way right now. So it depends on what, on epsilon and the set C. Yes. Instead of sub-indices, I write them as arguments. Well, so it was how it was. It was this way, and where it was epsilon.
No, just C epsilon on the.
Okay. And here. Okay. But you know, a family and a mapping is the matter is whether you use this as a family or a mapping. But the a family and the mapping is a synonym. So let's write as you like. The sets form a base of 0 in G. So this is sign of symmetry between gamma and G, the first sign probably. Up to this point, already the inversion theorem is a sign of symmetry, but up to this point still we had some statements about G and some other statements about gamma, and they didn't coincide. This shows that everything coincides. So let V be a neighborhood of 0 in G, and I need a symmetric neighborhood W, compact neighborhood of 0 such that W minus W is included in this V. Okay? So this is another neighborhood of 0, and this is symmetric this time. So let f be the characteristic function of W, it's easier to write the formula, not quite the characteristic function, but divided by this R measured to the power 1/2. So this function is normalized in L2. Yes? So then the normal f in L2 of G is equal to 1. And then consider what we already considered today many times. This is the convolution of f and f tilde. So this is a positive definite function. This is a positive definite function, as always when we take a function in L2, then such convolution is positive definite. Also we have this formula which we already used many times. So the Fourier transform of this function G is non-negative. By the way, do you recognize this on the unit circle or on the line? On the unit circle. What corresponds to this on the unit circle, basically? The fair kernel. Fair kernel. So if you take the neighborhood of 0, which is equal to the interval from -n to n, and if you convolve such a function with itself, then you obtain precisely the fair kernel. Not on the unit circle, on the group Z, of the group of integers. Yes, so if you take the characteristic function of some symmetric interval and then convolve it with itself, you obtain precisely the Fourier coefficient of the fair kernel. You know that the fair kernel is non-negative, and normally this is proved by some calculation with trigonometric sums, but in fact this is simply a consequence of this fact. So we consider this discrete function on integers and take it inverse Fourier transform on the unit circle, and this is a square of something. So this is a fair kernel. Now the inversion theorem applies to G, and in particular we have the following formula. This is the inverse Fourier transform. So this is equal to g of 0. So in general, if we put here character gamma of x, then we obtain g of x. And if we put x equal to 0, we obtain g of 0. And g of 0 is equal to 1. Which follows from the definition. So if you convolve this f with itself and calculate this as 0, you obtain precisely the integral of f squared. And the integral of f squared is equal to 1. Okay. Now this being done, we see also this function. Okay. So this integral is equal to 1, and g is non-negative. Then there exists C, a subset of gamma, which is compact, and such that the integral over C of g bar gamma d gamma is greater than 2/3. So some compact set C, well, here we should write C. Some compact set C on which the integral of this function is almost 1. Well, I could write, say, 9/10 probably, which would be better, but 2/3 will suffice. And after that, we can write the representation for g. This is the integral over c plus the integral over gamma minus c g hat of gamma gamma of x d gamma. Well, so we split this integral into two parts, now suppose that our gamma is such that 1 minus gamma of x is smaller than 1/3. So we take 1/3, okay. No. Sorry. So no, sorry. No. Suppose that x is such that we have this for gamma in C, so that our x in the set U C 1/3. Suppose we have this, then the real part of gamma of x is greater than 2/3, surely. Because we have this, then the real part of gamma of x must be greater than 2/3. So the integral over c of this function, well, I remind you that, okay, so this is this is non-negative, so we can put the real part here, the integral over c of the real part. The real part, and this is also negative, so the real part of gamma. Let's write this. We can put real part here without any hesitation, because this is real. Now we obtain this integral, and this integral will be greater than or equal to 2/3 the integral over c g hat, and so this is again 2/3, so this is 4/9 at least. Well, sorry? Why?
You have 2g as gamma.
Well, not g, only one. So this is 4/9. And over c prime, the integral over c prime is less than or equal to 1/3, or even strictly less than 1/3, because of this inequality. Well, I follow the author, and he adjusted the numbers very carefully. If I put 9/10, it would be much better, but but anyway, we have that g of x is greater than 1/9 for x in n of c 1/3. Okay. Well, so if we have x in this neighborhood, then definitely g of x is positive, and this function g is supported. Its support lies in v, in the initial neighborhood from which we started. So this x must be in v. Okay. So all x which lie here are in V, so this set U C 1/3 lies in V, and so we have obtained some neighborhood in the form we need in the prescribed neighborhood of 0. So that's the finish. Now, probably the last thing I can tell you today is this adjustment of the Haar measures of a group and the dual group of G and gamma in some classical cases. If say G is equal to the unit circle, then gamma is equal to the integers. And we normalize the Haar measures in this case like this. The Haar measure of the unit circle is equal to 1, and the Haar measure on the integers is simply the counting measure. It is equal to 1 at each particular point. And it is clear that here the inversion formula is true. Well, when we write the usual Fourier representation formula, we see that everything is consistent, and this normalization gives us a proper inversion formula. So if you normalize the Haar measure in the circle by 1, we make it a probability measure, then we must normalize the discrete measure on the dual group to be the counting measure. And the same is true for every compact group G. The same is true for every compact group G. So they are adjusted in this way. As to the group R, say, so we have, so any Haar measure there is some constant times Lebesgue measure. So we have the group R, its dual group is also R, and we have, say, Lebesgue measure on one copy of R and some constant times Lebesgue measure on the other copy of R. And how to adjust the constant so that the inversion formula be true? In fact, we know how, you know how, and this follows from the Gaussian integral. Well, the point is that we know how, but I don't remember how precisely. If we consider the Fourier transform of the function of this function, this can be calculated, and you know that this is equal again to e to the power minus some constant c x squared. I don't remember precisely what c is. This is pi times some 2 pi.
Maybe if it is minus x squared over q, then we are getting.
Yes, but you know, very often people put 2 pi here.
Yes,
well, so if I don't put 2 pi, I'm completely lost. But anyway, this is known. So we know the Fourier transform of this function, and it is basically the same function. So when we write the inverse Fourier transform of this one, we can easily calculate what we should put here, what constant we should put here, alpha. To have this inversion formula. So this is well known, easy, but I don't remember, especially when there is no 2 pi here. So this is also known.